You know, 3 oxygen atoms must combine. Each oxygen atom has 2s2, 2p4 configuration. So 2s2, 2p4. So when 3 oxygen atoms are to combine, first initially the deal is between the first 2 oxygens. They talk to each other and confirm that each one will have 2 unpaired electrons. So these 2 unpaired electrons, these 2 unpaired electrons become 2 pairs. 2 pairs are shared between 2 oxygen atoms. A double covalent bond is formed. So this part is over. Now each oxygen is left with how many lone pairs? 2 lone pairs. Now the third oxygen is question mark. It is looking at how selfish the first 2 oxygens, and without considering the third oxygen, they themselves form a double bond and become stable. Then the third oxygen asks, what happened to me? I also want to combine with you to form a bond. Then they advise, okay, you do one thing. Against Hund's rule, you pair your unpaired electrons and provide a vacant orbital. So 2 unpaired electrons become 1 pair and provides what? A vacant orbital. To this vacant orbital, oxygen donates lone pair. That results in coordinate covalent bond. So finally, in O3 molecule, there is a double bond, there is a coordinate covalent bond or dative bond. This is the structure of O3 molecule. Without arrow also we can represent. Without arrow, how we write? O double bond O. Normal covalent bond with oxygen. Donor is given plus charge. Acceptor is given minus charge. So dative bond is represented in 2 ways. With an arrow pointing from donor to acceptor. This lone pair is donated. Or without arrow, donor atom is given positive charge, acceptor atom is given negative charge. You can write one resonating structure. This negative charge shift, this pi bond shifts. So this O become O minus now. This become double bond. Because of this resonance, the O bond lengths are identical. Actually, double bond and single bond, their bond length should be different. But both bond lengths of ozone are 128 picometers. Why the bond lengths are identical? Because of resonance. Now, finally, if you look at ozone molecule, it has a positive charge and a negative charge. It has polarity. Because of polarity, ozone is more soluble in water than oxygen. Write this point. O3 is more soluble. O3 is more soluble in water than O2. Ozone is more soluble in water than oxygen. Reason due to its polarity. Due to its polarity. Regarding the allotropes of sulfur, sulfur rhombic, sulfur monoclinic, sulfur plastic, colloidal sulfur, flowers of sulfur, angels sulfur. Many sulfurs are there, but first four are a little bit of importance in the examination, especially regarding colloidal sulfur. You have a very important point. When H2O, H2S, aqueous, is treated with sulfur dioxide, you get H2O plus S. H2O plus sulfur. Now to balance this 2H2O, 2H2S and 3S. Now the importance of this reaction, very very important. Here sulfur is -2, here it is +4, here it is 0. So -2 to 0, oxidation, +4 to 0, reduction. Same sulfur is undergoing both oxidation and reduction, disproportionation, but the question is not about disproportionation. Whatever the sulfur formed here, it is in the colloidal state. So the laboratory colloidal sulfur is prepared by passing SO2 gas into an aqueous solution of H2S. This is one important point. Another important point is, now here SO2 is undergoing what? Plus 4 to 0 means it is undergoing reduction. The one which undergoes reduction acts as oxidizing agent. So this is the only reaction where SO2 acts as an oxidizing agent. Generally SO2 acts as a reducing agent. So this is also in the exam they are asking. With which of the following, when SO2 reacts, it acts as an oxidizing agent? So one of the options is H2S. So when SO2 reacts with H2S, it acts as oxidizing agent. In all the remaining cases, it acts as reducing agent. So rhombic and monoclinic sulfurs both have a similar structure. You say it is a puckered ring structure. So 8 sulfur atoms, 1, 2, 3, 4, or 6. It is only 6 sulfurs. But actually, yes, sulfur rhombic must contain 8 sulfurs. We will change its structure. It is also called crown shape. Eight sulfur atoms. So it is called S8 molecule. Because in yesterday's lecture or the previous day, we already discussed that after carbon, sulfur is the second most catenating element. It forms self-linkages and form long chains or rings. So rhombic and monoclinic will have S8 ring structure. Now when it is heated, when rhombic sulfur or monoclinic is heated, depending on the temperature, it may break into S6 or S2 molecules. That S6 molecule will have a chain-like structure. This is the molecular structure of S6. Here we write one more important point. S2 molecule will have paramagnetic nature. We have paramagnetic nature, like O2 molecule. This is also important. Whenever I say important, you put a star mark. And when sulfur is melted and poured in cold water, you will get plastic sulfur with open chain structure. When rhombic or monoclinic are melted and the molten liquid is poured in water, and the molten liquid is poured in water, plastic sulfur is formed with open chain structures. When sulfur, rhombic or monoclinic is melted and poured in water, we will get plastic sulfur with open chain structures and have the property of elasticity. That's why we call it as plastic sulfur. Rhombic sulfur is the standard state of sulfur. Rhombic sulfur is the standard state of sulfur. What is meant by standard state? The previous chapter, thermodynamics, we discussed standard heat of formation. Most stable form. Under what conditions?
25 degrees Celsius.
Very good. So the most stable allotropic form of an element at 25 degrees centigrade and 1 atmosphere pressure is called standard state. We have taken standard state of carbon as graphite. Similarly, standard state of sulfur is taken as rhombic form. It is the most stable form at 25 degrees centigrade and 1 atmosphere. Here, again I am rounding off this rhombic. And I will ask you, what is the covalency and oxidation state of sulfur in S8 molecule? Very good. Covalency to oxidation state 0. Like yesterday we discussed about phosphorus. Number of covalent bonds is covalency. Here each sulfur is bonded with, each sulfur form 2 bonds with other sulfur atoms. That's why covalency is 2, oxidation state is 0. Now write the heading, hydrides. H2X type covalent hydrides. H2X type covalent hydrides. Means oxygen form H2O, sulfur form H2S, selenium forms H2SE, H2TE, H2PO. So what is the hydride of oxygen? Water. What is the hydride of sulfur? H2S, hydrogen sulfide. Similarly for selenium, hydrogen selenide, H2Se. For tellurium, hydrogen telluride. Polonium, hydrogen polonide. Now top to bottom, as the size of atom increases, oxygen is a small atom, so when it bonds with hydrogens, these bonds are strong bonds. Smaller atoms form stronger bonds due to effective orbital overlap. If you come to tellurium, tellurium is a very big atom, very big tellurium, and very small hydrogens. No matching. Central atom is too big, bonded atoms are too small. The bonds orbital overlap is not effective, so bonds are very weak. So down the group, same point we discussed in the 15th group also. From ammonia to bismuthine, thermal stability decrease. Here also, thermal stability means when you heat, how much stable they are. That is called thermal stability. Thermal stability follows the order H2O greater than H2S greater than H2SE, H2PO. This is the decreasing order of thermal stability of the hydrides. What about Bronsted acidic strength? Bronsted acidic strength. What are Bronsted acids? The one which gives proton donors. Which will donate proton most easily? Of course, this is radioactive, you can remove it. So the one which is having weak bonds can easily give proton. So top to bottom bond strength decreases. So ability of donating proton increases. So the answer is H2TE greater than H2SE greater than H2S greater than what? Reducing ability. reducing ability. So what is a reducing agent in terms of hydrogen atoms? The one which gives hydrogens is called a reducing agent. So hydrogen, same order will be same. H2Te can give hydrogens easily because the bonds are weak. In H2O the bonds are strong. Thus it cannot give hydrogens. So bond angle H2O greater than H2S greater than H2SC greater than H2T. Bond angle. In water, what is the bond angle? 104.5 degrees. Means close to 109. That's how we propose sp3 hybridization for oxygen in water. But in H2S, H2SC, H2Te, these bond angles are close to 90 degrees. Similar point, same point we discussed in the earlier group also. In ammonia the bond angle is 107 degrees, but other hydrides of 15th group, phosphine, arsine, stibine, bismuthine, their bond angles are very close to 90. Whenever bond angles are close to 90, it is due to pure p orbitals are involved in bonding. Pure p orbitals are involved in bonding. In the first hydride, that is water, the bond angle is 104.5 degrees. That indicates sp3 hybrid orbitals are involved in bonding. What about polarity? Down the group, bond polarity. As electronegativity decrease, bond polarity decrease. When bond polarity decrease, dipole moment also decrease. So write a point in both 15th and 16th groups. In both 15th and 16th group hydrides, in both 15th and 16th group hydrides, top to bottom, the bond polarity decrease. Hence the dipole moment also decreases. So why first decreases, later increases? Same point we discussed in this 15th group hydrides also. Ammonia to phosphine, boiling point decreases. arsine stibile. So these two are similar. So why first decrease, later increase? The reason is very simple. In case of first hydride, in both 15th and 16th groups, the first hydride of 15th group is ammonia. The first hydride of 16th group is water. So in both of them, you have intermolecular hydrogen bonds. Intermolecular hydrogen bonds. Oh, I thought you are the person. Your sister. Okay. So in both 15th and 16th groups, in case of the first hydride, why the boiling point is more? Due to intermolecular hydrogen bonds. But if you come to the second hydride, that is phosphine in 15th group, and H2S, hydrogen sulfide in 16th group, suddenly the boiling point decrease. Because in the second hydride there are no hydrogen bonds. In the first hydride there are hydrogen bonds. What type of hydrogen bonds? Intermolecular hydrogen bonds. Now after second hydride, why again the boiling point increase? So the answer is due to increase in molecular size and also increase in London dispersion forces or van der Waals forces. So very clear-cut reason. First hydride to second hydride, boiling point decrease because first hydride has intermolecular hydrogen bonds, second hydride has no hydrogen bonds. From second onwards, again the boiling point is increasing. Why it is increasing? Due to increase in molecular size and increase in surface area. That's why thereby the increase in van der Waals forces or London dispersion forces. So finally in the 16th group, the boiling point order H2O greater than, H2TE greater than, H2SE greater than, H2S. So water has 100 degrees centigrade as boiling point. H2S will have the boiling point negative value. In 15th group, here, this will be more dominating. So SbH3 greater than ammonia, greater than arsine, greater than phosphine. Here one more common point. In both 15th and 16th groups, the second hydride will have the lowest boiling point. What is the second hydride in 15th group? Phosphine. What is the second hydride in 16th group? H2S. So here phosphine will have the lowest boiling point. Here H2S will have the lowest boiling point. The one having the lowest boiling point, will be more volatile. The one with the lowest boiling point will have more volatility or volatile nature. In the exam they are asking this also. What is the most volatile hydride in 15th group? Phosphine. What is the most volatile hydride in 16th group? H2S. This is having lowest boiling point. Means highest volatile nature. Highest volatile. Now, oxygen not only forms H2O, it forms another hydride called hydrogen peroxide. Sulfur, not only it forms H2S, it forms H2S2, H2S3. H2O2, hydrogen peroxide, will have an open book structure. Open book structure. H2S2, hydrogen persulfide, will also have same open book structure. So both H2O2 and H2S2 will have open book structure. Here one more important point. The formation of large number of hydrides of sulfur is due to its catenation property. Sulfur has the catenation property. Thus it is forming large number of hydrides. Now selenium, tellurium, polonium, they form only one type, H2X type. In the laboratory, H2S is identified by In the laboratory, H2S is identified by number 1, by exposing the gas to a filter paper which is dipped in this is lead acetate. Immediately you will get a black precipitate of PBS. So the best way to identify H2S, though it has a rotten egg smell and highly poisonous, H2S is as poisonous as carbon monoxide. But people won't die in the atmosphere of H2S because of its strong rotten egg smell. By just noticing that smell, immediately we move away from it. So smell saves us. Whereas carbon monoxide, which is equally poisonous, it has no odor or no smell. That's why human beings or animals will easily die in the atmosphere of carbon monoxide. Next point, H2S is the group reagent H2S is the group reagent in the qualitative analysis for the detection of cations. Next point. H2S is a group reagent for second group in acidic medium. H2S is the group reagent for second group cations in acidic medium. Actually, H2S, 2H plus so in second group, cation analysis. What is the group reagent? H2S in which medium? HCl medium. So H2S is a weak acid. Thus it ionizes and give H plus and S2 minus ions, which is in equilibrium. But HCl is a strong acid. Thus it completely ionizes. This is a weak acid. So due to common ion effect, H plus are common. Due to common ion effect, the equilibrium shift in the backward direction. Equilibrium shifts in the backward direction, and hence the sulfide ion concentration will be less. So this H plus are common. So whenever more H plus ions are in the right side, equilibrium disturbs. It wants to lower the number of H plus ions. Thus it shift in the backward direction. When it shifts in the backward direction, this S2 minus ion concentration become low. At low concentration of S2 minus, S2 minus, the ionic product exceeds, the ionic product exceeds the solubility product. Whenever ionic product exceeds solubility product, what happens? Precipitation occurs. Ionic product exceeds the solubility product, hence precipitation occurs. Next, second group cations. Mention the second group cations. Many are there second group cations. but all are not important. Mainly these first four are important. Next, H2S is the group reagent. H2S is the group reagent. In fourth group of cation analysis, in the fourth group of cation analysis, that too in basic medium. That too in basic medium. So H2S plus NH4OH so here H2S 2H plus NH4OH plus NH4Cl. Now this NH4OH also undergoes so this H plus and OH minus, they form water. When H plus ions are removed from the right side, to fill the gap, the equilibrium shift in the forward direction. Earlier it shifted in the backward direction in second group, but in the fourth group of cation analysis, the equilibrium shift in the forward direction. So the concentration of S2 minus become more. At higher concentration of S2 minus, the cations of fourth group are precipitated as sulfides. So write the same point. Same point. In fourth group, when H2S in fourth group H2S is passed into the original solution, in the presence of ammonium hydroxide and ammonium chloride. And in the H2S equilibrium, as it shifts towards right side, the S2 minus concentration become more. And at this higher concentration of S2 minus, and at this higher concentration of S2 minus, the ionic product of fourth group cations, the ionic product of fourth group cations exceed the solubility product. Exceed the solubility product and hence precipitation occurs. So second group and fourth group. So total scenario, you have two scenarios. In second group, we already mentioned some cations. Pb2 plus, Cu2 plus, Hg2 plus, cadmium 2 plus, arsenic 3 plus, arsenic 5 plus, antimony 3 plus, Sn plus 2, Sn4 plus. Similarly, in fourth group, you have nickel plus 2, Zn plus 2, cobalt plus 2, manganese plus 2. You have qualitative analysis in our syllabus. That's why I am discussing at this point. Because here we are discussing about H2S. And H2S plays a key role in both second group and fourth group. So what is the group reagent here? Group reagent. H2S in acidic medium. HCl. Things here S2 minus ion concentration. Will be low as the equilibrium shifts in the backward direction. Shifts in the backward direction. Here the same point, S2 minus concentration is more, as equilibrium shifts in the forward direction. So two cases. So at low concentration, of S2 minus, the ionic product exceeds the solubility product, and these are all precipitated as their sulfides. Here also sulfide precipitates. Sulfides are precipitated. But here at high concentration, S2 minus. That's why they don't interfere here and there. A fourth group cation never be detected in second group. A second group cation is never detected in fourth, because both are different scenarios. In second group, H2S is passed in acidic medium. In fourth group, H2S is passed in basic medium. In second group, H2S in acidic medium will give low concentration of S2 minus, sulfide ion.
What are ionic product and solubility product?
Very good question. Solubility product. Product means multiplication. So what is the meaning of product? Multiplying. So solubility product actually, the word solubility product is used for sparingly soluble salts. The word solubility product is used for sparingly soluble salts. Some salts are slightly soluble, which are called sparingly soluble. When they are slightly soluble and give some ions, the ions are in equilibrium with the undissolved salt. So there I mentioned PbCl2 is a sparingly soluble salt which breaks into Pb2 plus 2Cl minus, not completely, little. Again the ions combine and go back. So forward and backward reactions both are occurring. Whenever forward and backward reactions occur at a particular time, the rate of forward reaction will be equal to rate of backward reaction. We say it is in equilibrium. So the product of molar concentrations of the ions of a sparingly soluble salt at equilibrium is called a solubility product. So solubility product constant Ksp is equal to active mass of Pb2 plus active mass of Cl minus whole square by active mass of PbCl2, which is equal to 1. That's why this is unity. You can neglect this. So Ksp if the solubility is S mole per liter, its solubility is also S mole per liter. Then here you can substitute S. Here it is 2S. Pb2 plus concentration S mole per liter. Cl minus concentration will be 2S mole per liter. So it becomes 4S cube. Ksp is equal to 4S cube, or S cube is equal to Ksp by 4, or S is equal to cube root of Ksp by 4, where S is called solubility. Ksp is called solubility product constant. So the difference between ionic product and solubility product, both are product only. Solubility product is the product of concentration of the ions at equilibrium. Ionic product is the product of concentrations of the ions at any other condition. At equilibrium we call it as solubility product. At any other conditions we call it as ionic product. So whenever the ionic product exceeds solubility product, precipitation occurs. So what is the principle? Whenever ionic product exceeds solubility product, precipitation occurs. Once again, I summarize. Please listen to the bullet points. We are discussing the hydrides of 16th group, in which H2S, which is a rotten egg smell gas, which is best identified in the lab, not by seeing its horrible smell, but just by exposing a filter paper dipped in lead acetate. So the filter paper becomes black due to the formation of black lead sulfide. And the next important point regarding H2S, it is a group reagent for two different groups in qualitative analysis. So what are those two groups? Second group cations and fourth group cations. To identify the cations of second group and to identify the cations of fourth group, actually these groups are not related to the groups of the periodic table. For convenience sake, cations are divided into different groups in qualitative analysis. They are nothing to do with the original groups of the periodic table. You should not confuse. So actually the second group is a very big group. Lot of ions are there. Suppose, what is your name? ROCKY. RAKI. Rocky One. Dr. Rocky One. Dr. Doc Chalk. Dr. Doc Chalk, Dr. Rocky Win, Dr. Kun Kinkisk. What is his name? Ken Mao. Kun Mao. Okay. So, second group is a pretty large group. We are asking Dr. Rocky One. Actually, Pb2 plus is a first group cation. But I mentioned in second group. Usually in qualitative analysis, Pb2 plus is mentioned in both groups. First group as well as second group. So why Pb2 plus is present in two groups? Actually it should be present in only first group. But equally we test for Pb2 plus in second group also. So that is a very, very, very important point. So actually first I will explain, later you can write a point on this. So what is the first group reagent? HCl. In qualitative analysis, to identify the cations of first group, we use a reagent called HCl. Now this HCl react with Pb2 plus of the first group and form PbCl2. This PbCl2 is not a perfect precipitate. It again dissolves and forms certain Pb2 plus ions. They again come into the second group. So this is the crux of this situation. So why Pb2 plus is present in both first group and second group? In first group it is not completely precipitated as PbCl2. PbCl2 is sparingly soluble. That's why Pb2 plus ions pass into the second group also. So write a question and answer. Why Pb2 plus? Why Pb2 plus is present in both first group and second group of cation analysis. Why Pb2 plus is present in both first and second groups of cation analysis. So the answer, Pb2 plus in first group is precipitated in the form of PbCl2. Is precipitated in the form of PbCl2 with dilute HCl. And this PbCl2 is not a perfect precipitate. And this PbCl2 is not a perfect precipitate and is a sparingly soluble salt. And is a sparingly soluble salt. Hence the Pb2 plus ions sneak into or come into the second group. Come into the second group. Now, so oxygen is also forming hydrogen peroxide. Though hydrogen and compound syllabus, in the syllabus it is removed, but as a hydride of oxygen of the P block, this H2O2 H2O plus O H2O2 2H plus 2 electrons H2O2 plus OH minus three OH minus ions. H2O2 2H plus 2 electrons plus O2. H2O2 plus O gives H2O plus O2. H2O2 gives H plus HO2 minus. HO2 minus H plus O2 2 minus. So how many I gave? 1, 2, 3, 4, 5, 7 I wrote here. So in the first one, H2O2 is giving a nascent oxygen. That's why it is an oxidizing agent. So in one, it acts as oxidizing agent. In two, into, it is accepting electrons. The one which accepts or gains electrons is an oxidizing agent. So in 2 also, it acts as an oxidizing agent, but in acidic medium. In 3, also it is accepting electrons, but in basic medium. So 1, 2, 3 represents, 1, 2, 3 represent H2O2 is acting as oxidizing agent. Now, look at 4th. In 4th one, it is giving electrons. It is a reducing agent. In 5th also, it is taking oxygen from others. It is a reducing agent. Sixth and 7th. Sixth and 7th represent the acidic nature of H2O2. It is giving protons, Bronsted acid. If you add both, you will get a net reaction. HO2, HO2 cancel. So what is the net reaction? H2O2 gives rise to 2H plus. This is the net reaction. It is a weak dibasic acid. H2O is a weak dibasic acid. When it is dibasic acid, what is the equivalent weight? Equivalent weight of dibasic acids is equal to molecular weight by 2, basicity. So molecular weight of H2O is 34. So equivalent weight of H2O is 17. H2O2 oxidizes lead sulfide to lead sulfate. Potassium iodide to, like ozone, just yesterday we discussed, similar properties. Nitrates to nitrates. Sulfides to sulfates. sulfides to sulfates, ferrous sulfate to ferric sulfate, potassium ferrocyanide to potassium ferricyanide. Of course, this is an acidic medium. This is also an acidic medium. Acidified dichromate in acidic medium oxidize it to blue color chromium peroxide. This is very, very important, seventh one. What is CrO5? Chromium peroxide. What is chromium oxidation number in chromium peroxide? Plus 6, correct, not plus 10. It has peroxy bonds. It has a butterfly-like structure. This is the structure of CrO5. This OO bond will have -1, -1. 4 oxygen atoms will have -1. 1 oxygen will have -2. So chromium is surrounded by 6 units of negative. Thus it will get 6 units of positive. Generally we calculate x minus 10 is equal to 0. X plus 5 into -2. Then you will get plus 10. But that is not correct. This is correct. So left side also chromium is in plus 6. Dr. Ricky Ponting. So when potassium dichromate, orange colored, is converted into blue color chromium peroxide. The oxidation state of chromium is not changed. But our heading is H2O2 oxidizes. Then who is oxidized here? In the seventh one, on the head of chromium, left side and right side, we mentioned plus 6, plus 6. So when chromium oxidation number is not changed, who is oxidized in that? So here, oxygen is oxidized. When H2O2 converts the orange colored potassium dichromate into blue color chromium peroxide in acidic medium, which one is oxidized? Oxygen is oxidized from -2 state to -1 state. H2O plus O. This O is responsible for antiseptic property. and disinfecting property. It is also responsible for bleaching property. Suppose, what is your name? Your name? Oh, Mark, easy to pronounce. So, Dr. Mark. Dr. Mark has taken some hydrogen peroxide liquid in his hand, put some ammonia also. This mixture he applied to the black hair. After a few minutes, the entire hair become golden yellow. Means the color of the black hair is bleached. So generally people go to beauty parlors to have their hair color bleached. Maybe the entire color may be, if he want to be a different fashionable person, the entire color can be converted into golden yellow. Or some strip wise, as you like. So one day one student came with golden yellow color this side and golden yellow color this side, two sides. So I asked him, do you add this color bleach with hydrogen peroxide? He said yes. Then why only two sides, this side and this side? That is my question. His answer is very interesting. So you want to ride a bike, and when he is going very fast on the bike, the hair will have a wavy nature, and this color on this side and this side, and more girls will see him. The glittering nature. So you want to draw attention from more girls, he told me. I said, okay, that is good, but the problem is you won't be in your control when you are riding a bike, expecting somebody seeing you, and the wavy nature and glittering nature of the sides of your hair may attract, you may attract some people. But you have to be alive for that. So most of the students nowadays, so they are blackmailing their parents and getting advanced high-end bikes and forgetting all the physics principles, moment of inertia, centrifugal force, centripetal force, road friction, grip, braking. So many physical forces are acting when you are riding a bike. So unless otherwise you take care of all these, naturally forces will balance with each other. But if you are exceeding the speed limits and without any control, automatically, obviously, you will met with an accident. That is more common nowadays in our country, because speed corridors are there. People are using high-speed cars, high-speed advanced mobiles, bikes. I think you heard about Narayana, Total India branch. It is a big college. Narayana and Sri Chaitanya are two giants in Andhra Pradesh. They started with small centers, spread to the entire country. Now they have lakhs of students. Maybe Narayana is having 5-6 lakhs of students. Maybe even if he knows, he will start a branch in Shillong also. So his only son. Because when this many branches are there, obviously he is very rich. And now he is a minister in the government, present government. Earlier government also is a minister. So he fetched a top-end car for his only son. The car is very, in terms of crores of rupees. I don't know which model it is. And in the wee hours means early hours, till late night they spend in bar, restaurants, pubs. Hyderabad pub culture is there. So he is riding this car with so speed, it almost crossed 200 km/h and lost control. And the metro rail pillar, the pillars are very strong. This car hit that pillar, just very near to his house. So though airbags are open, so both the occupants were instantly killed. And I think you know cricketer Azharuddin, former Indian captain. You haven't heard about Azharuddin? Maybe 10 years back, 15 years back, he is one of the top players for our country. He is from also Hyderabad, Azharuddin. Later he became joined Congress, became an MP. Now he is in politics now. He retired from the cricket. He is a politician now. Once he elected from Lucknow, I think. Lucknow or Moradabad. Once he elected from Hyderabad. But previous election he lost. Okay, his son also. In this case, he is not driving a car, but a bike. A high-end bike. Nowadays, governments are making this outer ring roads with 6-lane, 10-lane outer ring roads. So you can run very fast, drive fast without control. He lost control and hit the road divider, instantly died. So I am telling all these, so you should be very careful. So, not you. This H2O2 and ammonia mixture is used as a hair bleach. The black hair is converted into golden yellow. Similarly, doctors use H2O2 for washing the wounds, teeth, infected ears. So when H2O2 comes in contact with your skin, the body temperature will decompose H2O2 into H2O plus O. That O is very powerful nascent oxygen that kills the bacteria. So it is an antiseptic property, disinfecting property, bleaching property. All these of H2O2 is due to its oxidizing nature. Ozone is also oxidizing agent. O3 gives O2 plus O. Chlorine in moist condition is also oxidizing. Cl2 plus H2O gives 2HCl plus nascent oxygen. But there is in our entire syllabus, there is only one bleaching agent which bleaches by reduction. That is SO2. So right, SO2 bleaches by reduction. SO2 bleaches by reduction, and it is a moist bleach. And the bleaching action is temporary. This is nascent hydrogen. Bleaches colored petals into colorless. Now in your entire campus, hibiscus, Malvaceae family, flowers are there. If you dip a flower in water, moist condition, and put in a jar of SO2, SO2 jar, SO2 gas is there. In the jar you put a moist flower, red color or pink, whatever it is, and tilt the jar 3-4 times, and the flower will become colorless. So here the color of the petals is bleached. The bleaching action is by hydrogen. It is by reduction. Most of the bleaching agents bleach by oxidation. The only bleaching agent bleaches by reduction is SO2. So what are the bleaching agents that bleach by oxidation? H2O2, ozone, chlorine, bleaching powder, CaOCl2. So what are the reagents? Ozone, H2O2, chlorine in moist condition, bleaching powder. All these bleaches by oxidation. The only substance which bleaches by reduction is SO2 in moist condition. This is a very, very important point. Here, when I talk about H2O2, some oxidizing properties, there is a link between H2O2 and stoichiometry. What is meant by 10 volume H2O2? What is meant by 20 volume H2O2? What is the volume strength of H2O2? What is meant by volume strength of H2O2? So that also I'll discuss for 5 minutes. This is our heading. 10 volume H2O2 means H2O2 means 1 ml of the sample gives 10 ml of O2. at STP. By the reaction 2H2O2 gives 2H2O plus O2. So what is the meaning of 10 volume H2O2? That sample, if you take 1 ml or 1 volume, which decomposes and gives 10 ml or 10 volume H2, 10 volume O2 at ST. Suppose 20 volume H2O2 means 1 ml gives 20 ml O2 at ST. What is meant by 30 volume H2O2? That sample 1 ml decomposes and give 30 ml O2 at ST. What is the percentage strength ten volume H2O2? You know, 10 volume H2O2 means 1 ml of the sample should give 10 ml O2 at STP. But percentage means you have to take 100 ml. Ten volume H2O2 of 100 ml. Why I took 100 ml? Because I want to calculate percentage. That's why I have taken 100 ml. How much oxygen will it give? 1 ml is giving 10 ml. Very good. So the answer is 1000 ml of O2 at STP. Once again I repeat, the first step, we know the meaning of 10 volume H2O2, which means 1 ml of that sample decompose and give 10 ml O2 at STP. Same 10 volume H2O2, but I have taken 100 ml of the 100 ml of it. So when 1 ml gives 10 ml, 100 ml gives how much? 1000 ml O2 at STP. This is step 1. In the second step, we write the balanced stoichiometric equation. 2H2O2 gives 2H2O plus O2. Means 2 moles will give 1 mole O2 at ST. 2 moles means 2 into 34 grams. Mole means its molecular weight. 1 mole means 1 mole of any gas at STP occupies 22.4 liters at STP. Now I read the sentence in the reverse direction. 22.4 liters of O2 at STP of O2 at STP is coming from how much? 2 into 34 grams. This line reverse. 22.4 liters of water at STP is coming from 2 moles of H2O2, 2 into 34 grams. But we got 1000 ml water at STP from 100 ml of the sample. So here I write 1000 ml. Achha, this is in liters. 1 liter. Okay, you also write 1 liter. So it will give 68 by 22.4. 68 by 1 into 68 by 22.4. So 68 by 22.4 means 3.03 grams per 100 ml. That is nothing but 3.03 percentage or approximately 3%. Once again I repeat, you don't follow. So I am solving a problem. My heading of the problem is, what is the percentage strength of 10 volume H2O2? What is the percentage strength of 10 volume H2O2? What is the meaning of 10 volume H2O2? 1 ml of that sample should give 10 ml water at STP. But I want to calculate percentage strength. I will take 100 ml and calculate how much oxygen it will give. I got 1000 ml O2. So I kept this part aside. But I have taken the balanced equation. In balanced equation, 22.4 liters of O2 at STP is obtained from 68 grams. But we got 1000 ml of O2 at STP, 1 liter of O2 at STP. Comes from how many grams? That gives 3.03 grams. This 3.03 grams is coming from how much? 100 ml of the H2O2 sample. That is only giving 1000 ml of O2. So 10 volume H2O2 means H2O2 means 3%. 20 volume H2O2 means 6%. 30 volume 9%. What is the molarity? Molarity of 10 volume H2O2. What is the molarity formula? Weight by molecular weight into 1000 by V in ml. What is weight? 3 grams by molecular weight 34 into 1000 by V in how much ml? This 3 grams is present in how much ml? 100 ml. That's why 3%. This gives 0.89 molar. Normality will be 2 into molarity. It is a dibasic acid. So 2 into 0.89. 1.78 normal. Now here, I advise the student, one single line will help. Lot of problems you can solve. That single line is 10 volume. Oh, time is over. It functions only around 2 hours. Okay, take a break. So this is the thing just we discussed. The percentage strength, molarity and normality of 10 volume H2O2. So 10 volume H2O2 is equal to 3%. That is identical equal to 0.89 molar. That is identical equal to 1.78 normal. This line is more important. Any calculation, suppose I ask you a very simple question. %, H2O2, 30% H2O2 is called perhydral. What is its volume strength? Very good. So 3% means 10 volume. 3% is equal to 10 volume. 30% is equal to how much volume? That is equal to 100 volume. So any problem you can solve if you are thorough with that particular line. 10% H2O is 10 volume H2O is 3%, which is 0.89 molar. That is equal to 1.78 normal. So after hydrides, now we go for oxides. They form two types of oxides, dioxides, trioxides. In the dioxides category, SO2, which is an angular molecule, sulfur is sp2 hybridized. Here we take sulfur configuration 3s2 3s2 3p3 3d1. This is called first excited state. Actual configuration is 3s2 3p4. I promoted one electron to D because sulfur is forming 4 bonds. 4 bonds means 4 unpaired electrons must be there, in which sulfur is undergoing sp2 hybridization. Hybrid orbitals always form sigma bonds. So this sigma bond is formed by these hybrid orbitals. How many pi bonds are there? 2 pi bonds. One pi bond is formed by the lateral overlap of p orbital of sulfur with p orbital of oxygen. That's why this bond is called p pi bond. Because 2 p orbitals are involved. Which p orbitals? P orbital of sulfur is overlapping with p orbital of oxygen. That's why the bond is called p pi. Now the other pi bond is formed by the lateral overlap of d orbital of sulfur with the p orbital of oxygen. That's why this bond is called p pi d pi bond. Now the question asked is, in SO2, question is over. In SO2, just listen, question. In SO2, option 1, 2 sigma bonds, 2 p pi bonds. Option 2, 2 sigma bonds, 2 p pi d pi bonds. Option 3, 2 sigma bonds, 1 p pi bond, 1 p pi d pi bond. Option 4, 2 sigma bonds, 1 p pi bond, 1 p pi d pi bond, 1 lone pair. Option 4 is correct. There is 1 lone pair, 2 sigma bonds, 1 p pi bond, 1 p pi d pi bond. Suppose if you come to SO3, in SO3 total how many bonds are there? 6. But it is a trigonal planar molecule, sp2 with 120 bond angle. When 6 bonds are there, You have to propose the second excited state. 3s1, 3p3, 3d2. Why I have to propose the second excited state here? Second excited state, the configuration becomes 3s1, 3p3, 3d2. Total how many single electrons? 6. Thus it can form 6 bonds, 3 into 2. What hybridization here also? Hybridization is based on the bond angle. Bond angle is 120 means trigonal planar. Whenever bond angle is 120, whenever it is trigonal planar, you have to propose sp2. I have to mix 1s and 2p orbitals, hybridized. So 3 sigma bonds. Hybrid orbitals always form sigma bonds. So 3 sigma bonds. The remaining 3 are pi bonds. So one pi bond is what type? P orbital of sulfur with the p orbital of oxygen. P pi, p pi. What about the remaining 2 pi bonds? So in SO3, three are sigma bonds. One is a p pi, so p pi, p pi. The others are p pi, d pi. This is also p pi, d pi. Because 2 d orbitals are involved in pi bonds, with whom p orbital of oxygen, d orbital of sulfur, then it becomes p pi, d pi. If both p orbitals are involved, sulfur p orbital, oxygen p orbital, p pi, p pi, 2 p pi, d pi bonds. So in SO3 total how many bonds? 6 bonds. 3 are sigma bonds formed by 3 sp2 hybrid orbitals. S and p are mixing with each other. When 3 orbitals mix, 3 hybrid orbitals will be formed. Hybrid orbitals always form sigma bonds. Pure orbitals will form pi bonds. What kind of pure orbitals? One is a p orbital. The remaining 2 are d orbitals. When this pure orbital, p orbital of sulfur, overlap with the pure p orbital of oxygen in a sidewise manner, p pi bond. Similarly, the other 2 will be p pi, d pi bonds. Next. SO2 can act as both Lewis acid and Lewis base. It can act as both Lewis acid and Lewis base. Where SO3 acts as Lewis acid alone. Just now I wrote the structure. SO2, because of this lone pair, it can be donated, act as a Lewis base. Lewis bases are electron pair donors. Same SO2, if the pi bond shift towards more electronegative oxygen, sulfur gets positive charge. So it can accept an electron pair. So it acts as a Lewis acid. Because it has the ability to donate electron pair, it can act as a Lewis base. Because when the oxygen, the pi bond shift towards more electronegative oxygen, the central sulfur will get positive charge. Then it can accept electron pair. Electron pair acceptors are Lewis acids. So it becomes HSO3 minus bisulfite ion or hydrogen sulfite ion. Whereas SO3, it has no lone pairs. What it will do, whenever the pi bond shifts, sulfur become positive. So when it become positive, it can accept an electron pair, forming HSO4 minus. So it is acting as Lewis acid. OH minus act as Lewis base.